So today we are going to continue our conversation. We're going to talk about selection sort. This is a little bit different. It is an in-place comparison. It's not very good with large lists, which is true of most of these. They're not very good with large lists. Most modern searches are none of these. The algorithms that we use for real to sort data is none of these sorts. But we kind of have to do baby steps as we go through this. So the selection sort works like this. You start going through the list, and you're looking for the smallest value in the list. And then you put it at the back of the list. So if we look at this list here, it's searching through, trying to find the smallest values. Finds 0, finds 1, finds 2, finds 3, finds 4, 5, 6, 7, 8, 9. So it's selecting the smallest value in the list. So take a look at this looping structure. And again, we're going to look at it to see what kind of structure we would need in order to accomplish this type of task. So pause the video, take a look, and then we'll come back to that. So if we look at this structure and kind of look at the trace here, we can see that the blue square goes all the way down through the list. It's going a specific number of times. Now granted, that specific number of times is decreasing each time. So that's your inside loop. That's a for loop. The outside loop, your yellow blocks, is going through a specific number of times, namely the full length of the list. So the structure for this is going to be 2 for loops. Not a while loop, 2 for loops. So we're going to loop starting at 0 and going all the way to, except for the last 2 elements, because we got to be able to handle a swap at the end. In each pass, swap the item at the jth index with the minimum item in the rest of the array. At the end of each pass, items in element 0 through element j are in ascending order, and each item in this sorted portion is the final position in the array. So looking at the code for this, it's 2 for loops. The outside for loop going through the entire list minus 1. Now the reason we need to subtract off 1 is because we have that j plus 1. We're looking 1 ahead. If we didn't subtract off 1, we'd walk off the end of the list at the very end. Then the inside loop is starting from where this one is left off, the minimum index, j. And it's go from there to the end of the list. That's that blue square that was traveling through. So it changes where it starts. First it starts 1 more than where this current one is. And it'll go through all the way through the entire list. So it's 2 for loops. So again, when you're studying for the AP exam and you're trying to study which loop this is, you see code that is a sorting algorithm that's 2 for loops. That's selection sort. You don't need to trace it. If you know how selection sort algorithm works, then there's no reason to trace the code. You just have to recognize it. When we do the insertion sort, right, we're looking for the while loop and the for loop. Right? So knowing what these code segments look like, not memorizing every bit of it, but knowing the 2 loops involved and the order in which they are involved, whether it's outside or inside, is going to be your key to avoiding tracing any of the sorting algorithms on the AP exam. Because they make this promise, you don't have to memorize code. And technically, no, you don't. You just have to be able to recognize code. That's a difference. Memorizing versus recognizing is definitely different. So this sort is not on the AP exam, which is kind of interesting that it's not, because it's used a lot. The Quicksort is clearly named Quicksort for a reason. It's a very fast sorting technique. you're not going to do much with this other than just kind of introduce it to you. I'm not going to show you code for it, but I wanted to show you what it does. Oh, I forgot to show you the video. Hang on. We got to look at our dancing video for the previous sort. So look at the dancing video for the selection sort. Forgot to play this video. So go ahead and watch this video, and then pause this video, and then come back to it. All right, so as I was saying, Quicksort is not on the AP exam. It's called a recursive algorithm. Now, we're going to talk more about recursion later. But a recursive algorithm is an algorithm that calls itself. So I'll give you a quick example of a recursive algorithm. Suppose we have the Statue of Liberty again. A whole line of people in the Statue of Liberty, and you're the very last person in line. And you want to know how many people are in front of you. Well, what you can do is ask the person in front of you, the person right in front of you, how many people are in front of you? And they say, well, I don't know. So they go and they ask the person in front of them, how many people are in front of you? They say, I don't know. Let me ask the person in front of me. So they keep going all the way up the stairs. So they get to the very, very top person, and the person behind us says, well, how many people are in front of you? And the person at the top of the stairs says, there's nobody in front of me. So then the person behind the person at the top of the stairs says, well, there must be one person in front of me. Then the person behind him says, oh, well, then there must be two people in front of me. And so forth, so you get all the way back down the stairs, and then you know, and you got your answer, how many people are in front of the list. The same question keeps getting answered. How many people are in front of you? That's the question we're asking. To find out how many people are in line, we got to ask how many people are in front of me. So we keep asking the question over and over and over again until we get to some tipping point at one end, and then we work ourselves all the way back down through the list. That's how recursion works. So if we look at this sort here, they're splitting the list and they're sorting the list based upon splits. We'll look more at this loop when we get to recursion. But I just wanted to introduce it as the Quicksort is probably the sort that you'll deal with when you go to college. That's the one that is the fastest for most of you. There are even faster than this, but this is faster than any of the other ones we talked about. Mergesort. Again, we have to talk about recursion for us to get into Mergesort. It's going to be pretty easy to identify on the AP exam. It's the recursive one, right? And you'll see what that means. But let's take a look at the video for a Mergesort so you can kind of see what a Mergesort looks like. This is on the AP exam. Instead of Hungarian dancers, we're going to go with the Transylvanian Saxon German folk dancing. So go ahead and watch this video. So that was Mergesort. Hopefully you watched that video. It looked really, the algorithm looks much more complicated than any of the other algorithms we looked at. But when we actually go ahead and look at the code, we're going to see it's actually fairly simple. The code to make that happen really is not that complex if you understand the process of recursion, which we'll take a look at later. So, the next thing we have to talk about is big O notation. Dun, dun, dun. Essentially, this is how many comparisons are going to be needed to complete the sort. This is one of our ways of comparing sorts. And it is based upon the worst case scenario. And you look at the execution time required or the space in memory required. So when you're looking at big O notation, it doesn't necessarily cover everything at once. You're looking at those two pieces separately when you're comparing loops. And again, we talked about this before, how we said, depending upon what you want to accomplish, you might sacrifice memory size for speed. You might use a lot of memory in order to get the job done really, really fast. Using a lot of memory for a short period of time versus having to use a little bit of memory for a long period of time makes a difference. You might be able to allocate a lot of memory for a short period of time and then free it up for something else. So let's go through these different designations. O1 describes an algorithm that will always execute in the same amount of time or space, regardless of the size of the input data set. So no matter how big the data set is, it's going to take the exact same amount of time. So here's a little example, a little comparison, a little bit of code. Doesn't matter how big that whole data set is, it's only looking at one element in the data set, namely the first one. And that line of code will always take the same amount of time to execute no matter what. No matter how big that array strings is, it's always going to take the same exact amount of time to execute. So that's O1. Yeah, O1's not very useful because you're not going to be able to do very much with it. It's just essentially an if statement. ON, haha, you were expecting O2. No, ON. ON describes an algorithm whose performance will grow linearly in direct proportion to the size of the data set. A single for loop. This is O sub n. So if you have to go through the data set one time, then the space required and the amount of time required is directly proportional to the number of elements in the list. 10 elements in the list, you're going to have to do 10 comparisons. So we call that ON. Again, looking at the worst case scenario. ON squared. An example of this would be 2 for loops. Worst case scenario, you would have to go through every element of the list every single time. So every element of the list taken twice would be n times n. Those of you who've taken statistics or even in the end of your Algebra 2 course might recognize that when you're trying to figure out the number of possible combinations for taking 2 elements, it's n times n. So if I have a 2-digit combination lock and each digit could be 10 different numbers, the number of possible digits would be 10 times 10 or 100. So this follows along the same type of idea. You have to sort through every possible combination of the array in order to sort it. So that's an O notation of n squared. Most of the loops we looked at today and yesterday have a big O notation of O squared. The more nested iterations we get to n3 and n4. If I had more for loops in there, more comparisons to do, this n value goes up. So it's a very straightforward polynomial relationship. So if you're comparing, two sorts, an n4 would require more time than an n2. And the one that would be the fastest would be an n. 2 to the n. Now this is a really interesting one. Because in the beginning, the very small sets, 2 to the n is a very small number. Smaller than n squared. But then it becomes much bigger and then just explodes exponentially. Get it? Exponent, because it's an exponential function. 2 to the n is an exponential function. Exponential functions start out really, really small. It's the old story. I want to get 2 pennies from you every single day. So today, you're going to give me 2 pennies. Tomorrow, you're going to give me 4. The next day, you're going to give me 6. The next day, you're going to be 8. How long will it take for me to get $10 million from you? You'd be surprised at how quick that happens. It's about a month. $10 million in about a month, just with pennies. Because in the beginning, it's a very small amount, but then each time it doubles. Because really, the day before this ends, you're giving me a couple $1 million a day. log n. So this goes the other way. Right? Logarithms start out really steep, but then level off. So this is really good for large data sets. Not so good for small data sets, but better for large data sets. So if we look at this, 10 items might take 1 second to complete. 100 items will take 2 seconds to complete. But a data set containing 1,000 items only takes 3 seconds to complete. So as we double that or multiply that by a power of 10 each time, we're really only taking an extra second to happen. So that would be a very powerful sorting algorithm for very large lists. We're not going to learn anything that is log n, but that's really the modern sorting algorithm for very large lists. Most of you would not have a list that large to sort, but if you did, that's what you would want to be looking at. So here is a graph of big O notation comparing all of them. So if we look in blue, we have O1, and this is the number of operations here on the left axis, and on the bottom axis we have the number of elements. So we can see that the number of operations for O1 go up very quickly as we increase the number of elements. For O log n, that stays really, really flat. We have a very minimal number of comparisons for log n across the board. So in the beginning, it may not be ideal, but by the time you get out to having 100 elements, log n is much faster. And then you can go ahead and compare all the other different ones, where we have n log n. That's a different one we didn't talk about, n log n. And then we have on, we have our n squared, we have our 2 to the n, we have our factorial. So all of these get sorted and compared in terms of what are you trying to accomplish? Because the recursive algorithms take a lot more memory. They take a lot of memory to accomplish, but they're really, really fast. Whereas something like n squared doesn't take much memory at all, but it's kind of slow. So you really want to sort that out and make decisions based upon what you're trying to accomplish. Again, comparing sorts and algorithms is largely dependent upon what's your purpose. You have to pick and choose and weigh the characteristics that makes each of those important. So in terms of our sorts, bubble sort is an n squared, but can be as low as an on. Insertion sort, n squared. Selection sort, n squared. Quicksort, n log n. That's the one we're going to look at when we get to recursion. See how much faster that is? Worst case scenario is on squared. So at its worst, it's better, it's just as good as bubble sort, insertion sort, selection sort. But at its best, it's n log n. So in terms of speed, that merge sort, or that quick sort, excuse me, is the fastest sort. That's why I put it up there for us to look at, just for this point of comparison. So we could get to, it's kind of boring to say, all right, they're all n squared. So now you have one of them that's not, and you can see, how that compares to the others on the chart. If we look at n log n in purple compared to the blue on squared, we can see that the n log n is significantly faster as the number of elements go up. As we have very little elements, down here closer to 0, we can see there's not a huge amount of difference between them. So at that point, you'd have to say, well, is the memory sacrifice worth the speed? So that's it for this lesson. There is a practice assignment and an exit ticket. I know this was a very long lesson, but it's a very important one. So actually, there's no exit ticket, just a practice assignment. So here is the practice assignment. It's pretty straightforward, but I want you to use, I don't want you to kind of cheat with this. I want you to really try to look at it and see if you can figure it out rather than cheating and kind of looking at the code somewhere. All right, because this could be a really, really quick 5-second thing if you look it up on the internet. Don't look it up on the internet. It doesn't help you. All right, really try to look at it and figure it out which sort is which. Okay? So a nice, simple little practice assignment before we head out to our break. So that's it.